So picking up where we left off last time, we're going to go ahead and proceed with an example. And for this example, we're going to perform the following. We are going to write the following second order diffie-q as a system of first order linear differential equations. Or diffie-qs for short. Okay, so that's the goal. We're going to convert a second order differential equation or problem into a set or a system of first order linear differential equations. And you'll find this technique will be used over and over again to help break down a problem into multiple steps. It also makes it much easier to solve and more efficient to solve with a computer and other numerical techniques. So the equation we will be using is 2y double prime minus 5y prime plus y equals 0. The initial conditions are y of 3 equals 6. And the other condition, since this is a second order system, is y prime of 3 equals minus 1. Okay. Let me go ahead and see if I can add a new page for you guys. All right. So here we are on our new page. All right. So let's go ahead and do this. The way we go about it is we write higher order differential equations or diffie-q as a system with what's known as a change of variable. And this is a very common practice and also a very common technique as well. Okay, so the way we do this, we start in the following way. You start by defining two new functions. Okay, and so the first function is going to be x sub 1 of t, okay, will equal y of t, all right, and x sub 2 of t is going to equal y prime of t. So you can see how those come about. Specifically, we look at the y double prime term and we say, okay, we have two initial conditions, so we can make some use of that by writing out what the second function, which is x sub 2 of t, will be equal to some derivative. And you'll find out how this, on its own, right here, is a linear function, right? That's a linear function itself. So we are inherently creating linear functions just by creating the simple change of variable. Okay. So with that stated, notice that if we differentiate both sides of these two equations, this is what we obtain. By differentiation, or differentiating both sides, we get y1 prime equals y prime. Well, we defined y prime. It's x2. It's pretty neat. And if we take the second derivative of x2, you'll notice something else that's pretty neat. This will equal y double prime. Okay? It has to, since x2 was already defined as the first derivative, so the derivative of the first derivative is the second derivative. And you know what this is, don't you? This is going to be minus 1/2 times y plus 5/2 times y prime. Let you take a moment to try to figure that out. I would highly encourage you to stop here and try to figure this out. But it won't be too hard. You'll probably notice immediately all you have to do with the first equation we had before is just solve for y double prime in the original equation, where we had 2y double prime minus 5y prime plus y equals 0. Just isolate y double prime and you'll see this come through. Okay? And then this will equal, after we do all of that simplification and substitution, you'll notice this is 1/2 x1 by the definition we have above, right? Plus 5/2 x2. What do you know? That's going to make our lives so much easier when we start solving systems like this. And we do this with all higher order differential equations. We start with a change of variable, and then we start defining functions so that we begin working with a set of first order linear differential equations. Okay, that's it for this video. In the next one, we'll go further and take it to the next couple steps to finish off this problem. See you soon.